From raw materials to a fully assembled giant electric motor, there are several manufacturing processes involved. 180 workers in up to 6 months are required to manufacture one of these motors. Let's look into the details. Stage 1. Engineering design. It all begins with engineering. The design team first analyzes the customer's requirements, considering factors like voltage, power output, dimensions, and efficiency. Next, they prepare detailed blueprints and perform extensive calculations involving power, torque, materials, and other critical factors. They design every component, ensuring it can withstand the motor's demanding operating conditions. The engineering phase is crucial because the entire manufacturing process relies on these detailed plans. Any changes during this stage can significantly impact the subsequent assembly, potentially delaying the project and increasing costs. To avoid costly mistakes, engineers conduct thorough life cycle analyses, considering material properties, manufacturing capabilities, and performance targets. They also work closely with other departments, like manufacturing and procurement, to ensure smooth production. Throughout this stage, they generate comprehensive documentation, including detailed drawings and specifications, which serve as the foundation for the entire manufacturing process. This meticulous planning ensures that when manufacturing begins, each step can be executed efficiently and effectively, ultimately resulting in a high-quality product that meets all of the customer's requirements. Stage 2. Stator manufacturing. The stator is the stationary part of the electric motor that houses the windings that carry the electric current. First, the core of the stator is constructed by stacking thin sheets of electrical steel, also called laminations. These sheets are chosen for their low reluctance, meaning they easily establish magnetic fields, which is essential for efficient motor operation. To prevent the sheets from shorting out the high-voltage winding, each sheet has an insulating layer between them. These layers consist of a thin, durable material that can withstand the harsh environment of the motor. The number of layers and the type of insulation used depend on the motor's size and voltage. Once the core is complete, the copper windings are inserted and secured in place. The windings are precisely coiled to fit within the stator and are held in place with spacers or wedges. The choice of copper is due to its high electrical conductivity and ability to handle high currents. However, the specific type of copper used depends on the motor's application and environment. For example, some motors may use oxygen-free copper to prevent corrosion, or may incorporate special alloys for enhanced conductivity at low temperatures. Stage 3. Rotor production. The rotor is the rotating part of the electric motor that interacts with the stator's magnetic field to produce torque. Its production begins with machining a solid steel shaft to the desired diameter and length. The steel is chosen for its strength and ability to conduct electricity, which is important for the rotor's function. Once the shaft is complete, it is fitted to the rotor, which typically consists of steel stampings or a solid steel forging. The rotor's surface is then machined to create the necessary air gap and fit with the stator. The copper or aluminum bars that will carry the current are inserted into slots in the rotor, and these components are held together using wedges or other securing devices. Like the stator windings, the rotor conductors are also precisely placed to ensure optimal performance once the rotor is assembled. It is dynamically balanced to ensure smooth rotation without vibrations. Balancing is achieved by adding small weights to the rotor until it rotates evenly, which is crucial for the motor's overall efficiency and longevity. Stage 4. Magnetic core assembly. With both the stator and rotor individually manufactured, it's time to assemble the magnetic core. The stator and rotor are lowered into a heavy steel frame, also known as the cradle, which provides mechanical strength and support to the entire motor. During this process, precise alignment is critical to ensure proper fit and operation. Once in place, the rotor is secured to the shaft using a coupling, which also allows for adjustments in shaft alignment. In larger motors, additional support structures may be needed to hold up the heavy rotor and ensure stability. The completed magnetic core is then thoroughly inspected to verify that all components are correctly aligned and secured. This assembly marks a significant milestone as it forms the heart of the electric motor and directly influences its performance characteristics. Stage 5. Insulation system. The insulation system is critical to prevent electrical faults and ensure the motor's longevity. Starting with the stator windings, Each winding is wrapped with multiple layers of high-voltage insulation. The type of insulation used depends on the motor's voltage rating and environmental conditions. Common materials include paper, plastic films, and epoxy resins. Each layer is carefully applied to provide an adequate level of insulation, while maintaining flexibility to avoid cracks or breaks. Once the insulation is in place, the entire stator is baked in a high-temperature oven to dry out any moisture and ensure the insulation bonds properly. Additionally, the stator is coated with varnish to further protect the insulation from mechanical damage and environmental factors. The rotor insulation is typically simpler as the conductors are solid and not as prone to mechanical stress. However, it still requires careful application to prevent faults and ensure long-term reliability. By the end of this stage, the motor should have a robust insulation system that can withstand the high voltages involved in motor operation while withstanding the test of time. Stage 6. Shaft and bearing installation. The shaft, along with its associated bearings, plays a vital role in supporting the rotor and ensuring smooth, low-friction rotation. Large alloy steel shafts are used for their strength and durability, capable of withstanding the torque generated by the motor. These shafts are precisely machined to ensure accurate tolerances and are dynamically balanced to minimize vibrations during operation. The bearings are equally crucial in reducing friction and supporting the shaft. These large bearings are often mounted at both ends of the shaft to provide adequate support for the heavy rotor. Different types of bearings are used depending on the motor's size, speed, and load requirements. Proper lubrication and regular maintenance are essential to ensure the bearings operate smoothly and extend the motor's lifespan. Stage 7. Cooling system integration. An efficient cooling system is critical to maintain stable operating temperatures and prevent overheating. Most motors use an air or water cooling system, although the specific method depends on the motor's size and power output. Water cooling is more effective at dissipating heat, but requires a more complex system of pipes and pumps. Conversely, air cooling is simpler to install, but may not be as efficient. Regardless of the cooling method used, the system must be tailored to the specific requirements of the motor to ensure optimal performance. Ducts, fans, and other components are integrated into the design to ensure efficient heat removal. This helps maintain consistent performance and extends the motor's service life. Stage 8. Casing and accessories. The casing, also known as the enclosure, is attached to the frame and provides a protective housing for the motor. It not only shields the internal components from external damage, but also helps maintain a clean and safe working environment. The specific type of casing used depends on the motor's application and the surrounding conditions. For example, some motors may require a waterproof enclosure to operate in wet environments, while others may need a dust-proof design for dusty environments. Along with the casing, terminal boxes are attached to provide access for connecting the motor's external wiring. These boxes are sealed to prevent the entry of moisture or foreign objects, and are often equipped with grounding provisions for safety. Various sensors are also integrated into the motor to monitor critical parameters such as heat, vibration, and current. These sensors provide valuable data for predictive maintenance and can alert operators to potential issues before they become major problems. Stage 9. Testing and trial run. Before the motor is considered complete, it undergoes rigorous testing and trial runs to ensure it meets all specifications and operates safely and efficiently. This stage typically involves several non-destructive testing methods to check for any defects or issues that could affect the motor's performance. Common tests include voltage, load, insulation, and vibration tests. Voltage tests ensure that the motor's insulation can withstand the intended voltage without breaking down. Load tests determine the motor's performance under different load conditions, providing insights into its efficiency and power output. Insulation tests verify the integrity of the insulation system, checking for any faults or weaknesses that could lead to electrical issues. Vibration tests evaluate the motor's stability and balance, helping to identify any imbalances or defects that could cause excessive vibrations or damage. If any issues are identified during testing, the motor is sent back to the assembly area for corrective action. Once it passes all the tests, the motor is ready for the final stage, delivery. But before that, it goes through a trial run. A trial run is a comprehensive test conducted in a controlled environment to ensure the motor operates as intended and performs up to the manufacturer's specifications. During the trial run, various parameters are monitored, including temperature, vibration, noise levels, and performance metrics. This helps identify any potential issues early on, allowing for adjustments and improvements before the motor is put into service. Stage 10, finishing and delivery. After successfully completing the trial run, the motor is prepared for delivery. The finishing touches may include painting the motor to protect it from corrosion and weathering. Depending on the environment the motor will be used in, a range of protective coatings can be applied. Some motors may require special finishes like epoxy or polyurethane for added durability. Additionally, any necessary nameplates or labels are attached to the motor, providing information about its specifications and operating instructions. Once the motor is complete, it is carefully packaged for transportation. The packaging should protect the motor from damage during transit and handling. Larger motors might be too heavy or cumbersome to be moved as a single unit, in which case they may be disassembled for easier transportation. Upon arrival at the customer's site, the motor is offloaded and prepared for installation. The delivery stage is a critical final step in the manufacturing process. It ensures that the motor reaches its destination in perfect condition, ready to be installed and used in its intended application. If you enjoyed this video, please do and forget to leave a thumbs up and subscribe so you won't miss any new videos. Thanks for watching.